On New Year's Eve, 1859, Edmond Lescarbault, a rural doctor from a small village outside Paris, is sitting at home, possibly looking forward to a nice New Year's Eve dinner with his family, when there is an unexpected knock at the door. On opening it, he is startled to find himself facing the imposing figure of Urbain Le Verrier, France's most famous astronomer and the director of the Imperial Observatory in Paris. Now, without so much as a how do you do, Urbain Le Verrier forces his way into Lescarbault's hallway, demanding to inspect his astronomical equipment. You see, Lescarbault, as well as tending to the aches and pains of his local community, is a keen amateur astronomer, and a week or so earlier, he wrote a letter to Le Verrier telling him about a strange object that he saw crossing the face of the sun earlier that year. Now, this letter so incensed Le Verrier that despite it being New Year's Eve, he immediately jumped on a train and just a few hours later was hammering on poor old Lescarbault's front door. So, what was all the fuss about? Well, Le Verrier had long been troubled by the orbit of the planet Mercury. Now, this image on the slide shows, hopefully this works, sorry, it's not turned on. What you see here is a transit of the planet Mercury across the face of the sun, as imaged by a NASA spacecraft. Now, Mercury had repeatedly embarrassed astronomers throughout the 19th century when they found that they missed its transit, sometimes by hours, in one extreme case, by an entire day. Now, in a universe that was supposed to run like clockwork according to Newton's law of gravity, a planet with such poor timekeeping was really very troubling indeed. Now, Le Verrier had recently solved a similar problem with the orbit of the planet Uranus by proposing the existence of an unseen eighth planet whose gravitational tug was subtly altering Uranus's orbit. And when astronomers pointed their telescopes at the point in the sky that Le Verrier told them, they discovered an eighth planet, Neptune. So Le Verrier thought, I can pull off the same trick twice, essentially. Perhaps the weird orbit of Mercury is explained by another ninth planet, this time in between the orbit of Mercury and the Sun. And so when he read Lescarbault's letter, he immediately thought, perhaps this rural doctor has actually discovered my hypothesized world. So hence he now finds himself in Lescarbault's hallway. So he submits his observatory to a sort of a thorough investigation. He finds it relatively satisfactory. Then he submits Lescarbault himself to an intense interrogation, the one account compared to the meeting of a lion and a lamb. And then, to top it all off, he goes around the village and demands character witnesses from Lescarbault's neighbors to check he's not being taken in by a confidence trickster. But by the end of the day, he returns to Paris convinced that his new planet has indeed been found. And on the 2nd of January, just a couple of days later, he announces to the world the discovery of a planet that he calls Vulcan, after the Roman god of fire. Now, this causes an international sensation, headlines all over France and Great Britain about the discovery of a ninth planet of the solar system. And Lescarbault finds himself catapulted from obscure rural doctor to being feted by the great and the good of the astronomical community, and he is awarded the Légion d'honneur for his discovery. Now, Le Verrier, based on Lescarbault's observations, calculates the next time that Vulcan should transit the sun. But when astronomers look for it, they don't see it. And this continues throughout the 19th century. Over a course of decades, a thorough search is made for Vulcan. Occasionally there are sporadic sightings, but no one manages to predictably identify where this planet actually is. And by the early years of the 20th century, astronomers are forced to accept that Le Verrier's hypothesized world Vulcan does not, in fact, exist. So what was going on? Well, there is still nonetheless a problem, an anomaly with the orbit of Mercury. So this is essentially what's happening. What you can see here in this little animation is a planet orbiting the sun. Now, Mercury, like all planets, orbits the sun in an ellipse. But this ellipse doesn't stay fixed in space. It actually precesses. So you can see that this ellipse is rotating. Now, this is due to the gravitational tug of other planets in the solar system. But when you predict the rate of this precession using Newton's law of gravity, you get the wrong answer. Mercury actually precesses slightly faster than predicted. Now, this is a tiny effect. Basically, this means Mercury performs an extra orbit 1 every 12 million Mercurian years. So we're talking about a 1 in 12 million anomaly. But nonetheless, it cannot be explained by Newton's law of gravity. Now, it turns out this anomaly had a far more profound implication than the discovery of just another planet. It actually was a clue to a radical new picture of space, time, and gravity itself. The solution was eventually found by this man. So this you'll recognize, hopefully, as Albert Einstein, but not as you're used to seeing him. This is him at the height of his powers in his 30s. And in 2015, he was putting the finishing touches to what would be his masterpiece, a radical new theory of space-time and gravity that is known as general relativity. Now, as a first test of his new theory, Einstein attempted to calculate the precession of Mercury's orbit, and he found an answer that exactly matched the astronomical predictions. Now, Einstein was apparently so overwhelmed by this that he actually had heart palpitations and had to lie down. This was the culmination of 7 years, essentially, of hard slog. And one of the nice things that Einstein said about this moment, he said, "It gave me an appreciation for the fastidiousness and pedanticness of astronomers that I used to make fun of in the past." Essentially, what this little anomaly was a clue to one of the most profound realizations in modern physics. General relativity transformed our understanding of the universe. It led to the Big Bang theory. It led to black holes, gravitational waves, and many more besides. And that is all from one small anomaly. Now, essentially, the reason that this anomaly shows up is because Einstein did away, in some sense, with the force of gravity. He said there isn't really such a thing as gravity. What actually happens is a massive body like the sun warps the fabric of space-time. So you kind of imagine, the classic analogy is to imagine space-time as a kind of elasticated sheet, and a heavy body like the sun bends space-time around it, and this bending is most extreme closest to the sun. And as Mercury is the innermost planet, that's where the difference between Einstein's theory and Newton's theory is most apparent. So I tell you this story really to illustrate the power of anomalies. Anomalies essentially are little deviations often from our expectation based on our current theories, and they can sometimes be the clue to profound insights about the world around us. And that's what this talk today is going to be about. It's also what my book, Space Oddities, is about. It's about anomalies both past and present, that are challenging our understanding of the universe. I'm going to begin with a quote that's very close to my heart. So this is a quote from the American science fiction writer Isaac Asimov, who says, "The most exciting phrase to hear in science, the one that heralds new discoveries, isn't 'Eureka, I found it,' but, that's funny." So I'm going to tell you about a bunch of, that's funny things that are going on in physics at the moment. But to begin, let me set the scene. So why do we actually think there are new things out there in fundamental physics to discover? We actually know a huge amount about the world. We've discovered a huge amount in the last century since the story I just told you. And our knowledge of the universe is encapsulated in two extremely successful theories that we rather boringly refer to as standard models. One is the standard model of particle physics. This diagram essentially represents the known elementary particles that make up the world around us, the forces that allow them to interact with each other. It's described by a very beautiful, elegant piece of mathematical theory. The standard model is one of the most successful theories in history. It explains everything from the structure of atoms to how the sun shines. On the other end of the scale, this is the theory of the very small. We also have a standard model of the very, very big. Now, we know from astronomy, from looking up into the universe, for example, looking at galaxies, that there is a large amount of invisible material out there in the universe. In the 1970s, astronomers discovered that stars orbit galaxies too fast for the amount of matter that we see to hold them gravitationally together. And this led to the realization that there's a large amount of stuff called dark matter, essentially some kind of invisible substance that provides extra gravity that holds galaxies together. And looking even further out to galaxies themselves, we see that the universe is expanding. And in the 1990s, it was discovered that this expansion is actually accelerating. And this led to the discovery of another dark thing known as dark energy, which is a kind of repulsive force that is causing the universe to get bigger and bigger at an ever-increasing rate. So this pie chart essentially represents what cosmology tells us the universe is made from. That 5% sliver you can see that's labeled atoms, that's us, that's the Earth, that's everything we can see in the night sky, every star, every galaxy, every cloud of dust or speck of dust. Now, that is what is described by the standard model of particle physics. So this tremendously successful theory of the microworld, which was really in some sense the closest we've come to a theory of everything, only describes 5% of what's out there. The rest of it, 27% dark matter, 68% dark energy, we have no idea what they are. And this is one of the primary reasons we believe there is more to discover in the universe. Now, This description of the universe is encapsulated in a theory known as the standard cosmological model, which essentially describes the history of the universe beginning with a very rapid period of expansion known as inflation, which gave rise to the Big Bang, and then the universe has been expanding ever since, with dark energy gradually accelerating that expansion later on in its history. So we have these two tremendously successful models, but in some sense they are in conflict with each other. The standard model of particle physics can't explain very much about what we actually see up there in the universe. So I'm going to tell you two stories tonight about two anomalies, one that comes from the very, very small scale, the world of particles, and another that comes from the grandest scales, the scale of the universe as a whole. So I'm going to begin with a demonstration. So hopefully you all were handed a little half of a pair, what looked like 3D glasses when you came in. So what I'm going to do, if we could lower the lights a bit, please. What I've got here is a hydrogen lamp. So essentially there's a little container of hydrogen here, and that's going to pass a high voltage electric current through. Now, what first I want you to do is just, I can only turn this for a short while, so if you hold up the thing to your eye and look at the lamp, I'll give it a little rotate so you can see it. And hopefully, also for those watching on the live stream, you'll be able to see this because the cameraman is going to kindly hold up the diffraction grating to the camera. What hopefully you can see are two lines. You don't see, or maybe it's not pointing at you yet, it's just coming round gradually. Can you see anything? People seeing something? Yeah? So what colors can you see? Fuchsia and red, yeah. So I'll just keep doing this a bit longer so you'll get a look. So what you're looking through is a diffraction grating. So what it's doing is breaking the light from the hydrogen lamp up into a rainbow spectrum. And what you see is actually, there are only really two prominent colors there. I'll turn that off. Thank you very much. If you didn't see it, that's what you should have seen. So what you are looking at there, you are seeing a quantum mechanical effect. You are seeing evidence with your own eyes of quantum mechanics. So what's going on? Well, you are looking here, in this, as I said, in this container there is hydrogen. Hydrogen is the simplest atom. It's a single proton orbited by a single electron. Now, according to quantum mechanics, electrons can't orbit a proton at any distance, like planets can orbit the sun. They can only orbit in strict quantized energy levels at certain distances, essentially, from the nucleus. Now, normally, hydrogen, the electron would be in the lowest energy states. You can see these various orbitals. The lowest one, labeled n equals 1, is the one the electron would normally be in. But by passing this this electric voltage through the hydrogen, you excite the electron up into a higher orbital. And then what happens is it falls down back into a lower orbital. So see, here we've got an electron going around in the third orbital. And if I press a magic button, it will then quantum jump down into the second orbital and emit a photon. So the photon that's emitted carries away the energy difference between those two levels. And that produces that red band that you can see. Another thing that can happen is the electron can be in the fourth energy level, and similarly, it can perform a quantum jump and fall down into the second energy level, and this time it gives off a sort of bluish photon of slightly higher energy. So that's what you're seeing. Those two lines you saw are essentially quantum jumps in a hydrogen atom. Now, there was a crucial anomaly that was discovered related to these very transitions back in 1947. And this discovery was carried out by a man called Willis Lamb and his assistant Rutherford. And essentially what they had done is they had spent their time microwaving hydrogen atoms. And in the process, they had discovered that in this second orbital that we can see the electron moving around in, which is the one that these transitions were taking place to, it wasn't actually a single energy level, but two energy levels with very subtly different energies. In fact, the energy difference was tiny. It was about 1 part in a million. Now, that may not sound like a big deal, but when Lamb went to this, so this is a picture of a conference that took place in 1947 on Shelter Island near New York, and it was the first major conference where the sort of the galacticos of the theoretical and experimental physics world got back together in the aftermath of the Second World War. Oppenheimer was there, for example. So what you can see here, Lamb is the guy leaning over the table, and there's an interesting discussion going on. In the middle is Richard Feynman, and on the right is Julian Schwinger. And Lamb's 1 in a million anomaly was actually a crucial clue that allowed Feynman, Schwinger, and various others to form what is now the basis of our understanding of the physical world. This was really the beginning of what we call quantum field theory. So quantum field theory says something rather strange, which is actually that particles like electrons and quarks aren't really, in a sense, fundamental. They're manifestations of much less tangible, more ethereal substances known as quantum fields. So you can think of a quantum field as kind of like an invisible fluid that permeates the entire universe. And in this picture, a particle like an electron is just a ripple, essentially, a vibration in this invisible field that fills the whole universe. So that means that every electron and every atom in our bodies is just a little vibration in this universal electron field that is all around us. Now, we know of about 17 particles in the standard model of particle physics. That means there are 17 fields. Now, this has a rather profound implication for what we mean when we talk about space. What do we actually mean by empty space in this picture? Well, what you would think of as empty space, imagine going to some distant part of the universe, intergalactic space, where there's very little stuff, and you build a box and you suck every stray atom out. You're literally left with nothing. What does nothing look like in this picture? Well, it actually looks rather interesting. This is a picture of nothing, an animation of nothing. So what you're looking at here, this is from the University of Adelaide, is a simulation of vibrations, of subtle quantum vibrations in these quantum fields that are always there in the vacuum. So essentially, even when there are no particles there, because of quantum uncertainty, these fields are constantly shimmering. They're sort of jittering like a gentle breeze on the surface of a pond. So you can see this incredible agitated quantum motion. And actually, what Lamb had seen, this subtle shift between these two energy levels in hydrogen, was actually the influence of empty space on the orbit of an electron as it moved around the atom. Essentially, in one orbit got buffeted more than the other by these quantum fluctuations and led to a very small difference in energy. And it was this crucial clue, this tiny 1 in a million anomaly, that led to this profound new understanding of the microworld. And quantum field theory is now the language with which we describe all of modern particle physics. So this is a huge moment in the history of physics. But I'm going to come on to the actual anomaly that's troubling physicists today. So the fact that the vacuum has all these quantum fields in it provides us with an incredible tool for probing things that we haven't yet seen. So I'm going to show you how we can do this. So this is a particle called a muon. Well, it's not really. It's a picture I drew of one. But a muon, you may not have heard of, it's essentially a heavy electron. So the muon is a partner of the electron. It's exactly the same as an electron, in fact, except it's 200 times heavier, and it doesn't live very long. Muons only live for about a millionth of a second, and then they decay. But there are actually muons in this room right now. They're produced by cosmic rays striking the upper atmosphere, and they fly through the Earth's atmosphere and down to the ground. So there are a few of them zipping through you at any one moment. Now, a muon, like an electron, is electrically charged, and it also has a property called spin. So this is essentially as if the muon is rotating on its axis. Now, thanks to Michael Faraday, we know that if you have a rotating electric charge, you also get a magnetic field. So Faraday did experiments where he passed electric currents around loops, a magnetic field is produced, a muon rotating behaves a bit like a moving electric current, and you get a magnetic field. Now, why is the magnetic field of a muon interesting? Well, this is why. The muon doesn't actually just sit there on its own in the vacuum. It's actually surrounded by all of these quantum fluctuations. So these sort of vibrations that are happening in these 17 fields that I discussed earlier. And this means that when you measure the magnetism of a muon, you're not really just measuring the magnetism of a muon, you're measuring the magnetism of a muon plus all its interactions with the quantum fluctuations in the vacuum. And that means that if there are new quantum fields that we've not seen before, for example, if there is a quantum field that dark matter is a vibration in, that dark matter field is also there in the vacuum, and it can contribute to the magnetism of the muon. So if you make a very, very precise measurement of how magnetic muons are, and then you do a very precise theoretical prediction of all these quantum fluctuations based on what we already know, and you see a difference, that subtle difference can tell you about the existence of potentially, say, dark matter or some other new force that we've never seen before. So this is a tremendously interesting thing to do. And indeed, physicists have spent decades making ever more precise measurements of this tiny little bar magnet that the muon carries around with it. Now, About more than 20 years ago, an experiment was conducted, one of the sort of latest in the series of experiments measuring this property at Brookhaven near New York. They used this big magnetic ring that you can see behind me. Essentially, they fired muons around the ring, and as the muons went around the ring, they measured how magnetic they were. And this is what they found. So the experiment measured the magnetism of the muon tremendously accurately. So this is a number, obviously. Don't worry too much about what it means. Well, the thing you should notice is it's quite a lot of decimal places, and this is the experimental measurement, and this was at the time the theoretical prediction. Now, if you compare these two numbers, you see that they agree pretty well until you get to the last 4 or so digits. So you have this disagreement essentially in the last 4 digits. Now, if you compare that, these measurements and the prediction actually come with what we call an uncertainty, which is an expression of how well we think we've measured the quantity or how well we've calculated it. So you can see the uncertainty, that is right at the end. The uncertainty is about 6.3, but the difference between these two is actually quite a lot larger than that. So I'm very pleased with this animation. So if you take these two things and you subtract them from each other, you get the difference between experiment and theory. That took a long time to do, actually. PowerPoint doesn't, anyway. And what they found when they did this calculation, that there was actually, the difference between theory and experiment was more than 3 times the combined uncertainty on the measurement and on the prediction. So this was potentially a clue to the existence of some new quantum field that we'd never seen before. So in principle, tremendously exciting. So this is around 2006 or so. Unfortunately, when you get an anomaly like this, you can't really immediately conclude that you ought to book a flight to Stockholm to be awarded a Nobel Prize, because there often are boring explanations for what you're seeing that aren't the discovery of some new force of nature. So boring explanation number 1 is that you made a mistake in your experiment. And this does happen. Now, physicists are very careful, and they try their best to do the best experiments they can, but you can never eliminate the possibility that you've missed something. So that's one option. The second option is that the result is a fluke. In other words, because you have some uncertainty on your measurement, that value that you got could have landed sort of anywhere, basically, in a band. And you may have just by dumb luck ended up, or bad luck perhaps, ended up with a result that was quite a long way from the theoretical prediction. So it could just be a fluke. The last option is that the theorist forgot to carry a 1. So what I mean by this is actually these calculating the magnetism of the muon is a fiendishly difficult thing to do. And it's very easy to make some incorrect assumption, or in fact, in one case, actually, with this very prediction, swap a plus for a minus. That actually happened and led people to think they were discovering something when they weren't. So all these 3 things can happen. So you have to eliminate these 3 options before you can conclude that you're really discovering something new. Unfortunately, by 2006, the old experiment at Brookhaven had shut down. It wasn't really going to be able to collect more data. So members of that original team got together and started planning a souped-up version of this, what became known as the muon G-2 experiment. This was going to be a brand new experiment built from scratch at Fermilab near Chicago. The only bit of the old experiment they were going to reuse was a superconducting ring that provided the magnetic field that the muons go around inside. So essentially what they had to do was ship this giant ring from Brookhaven down the Atlantic seaboard of North America, around Florida, through Hurricane Alley, and then up the Mississippi River on a barge, all the way essentially to suburban Chicago before it was put onto a big truck, and they closed the freeways and brought it into Fermilab. And here's a nice little video from Brookhaven. This is the ring being removed from Brookhaven. You can see it's a bit of an operation. It then gets loaded onto this flatbed truck and wrapped in white plastic to protect it. Now, there's a funny story about this, which is that there was a rumor, a sort of urban legend on Long Island, that in the 1960s, a UFO had crash-landed. And it had been immediately whisked away behind the walls of Brookhaven Laboratory by the white coats. And then lo and behold, decades later, a thing that looks for all the world like a flying saucer emerges from the gates of the laboratory. Now, it didn't help that the moving company actually stuck a little green alien on what looks like the cockpit. Chris Polly, who was the spokesperson of the experiment when I interviewed him for the book, told me that they told local residents who set up deck chairs to watch this strange procession in the middle of the night. And one guy came up to him and said, "You can't tell me that's not a frickin' spaceship." Anyway, it wasn't a spaceship, it was a magnet. And it arrived at Fermilab. was installed. They completely rebuilt the experiment. All kinds of, this experiment is extraordinarily sophisticated. Chris described it as being like a 600-ton Swiss watch. You have to measure the strength of your magnetic field incredibly accurately. The detectors were already built, the temperature and humidity control in the building down to the nth degree. So a really impressive experiment. So this is how it works. So now, Dan, I need you to come on and bring me a rope. This is not because the talk's going really badly, I hope. Thank you. So this is where it all goes wrong. So what I'm going to try and demonstrate to you is basically how the muon G-muon experiment works. So remember, we said the muon is spinning. And so to represent the muon, I have this bicycle wheel. So what happens essentially is you have muons that are fired into this magnetic ring, and they are all polarized, so they're sort of spinning, their spin axis is in their direction of travel. So they're spinning in one direction. So if I spin up this bicycle wheel, hopefully this will work, and I let it go, this is what we call precession. So you can see that the wheel precesses, it rotates. Now, unfortunately, the rope's moving around a bit, which slightly hides the effect. But essentially, as the muons go around the ring, they do the same thing that this bicycle wheel is doing, and their axis of rotation precesses in the magnetic field. So you can see on the little diagram, this is going to hit me in the face, that they're shifting angle, and the rate at which they precess tells you how strong the muon's little bar magnet is. So by measuring the precession rate, you measure the magnetism of the muon. So that is basically how the thing works, right? Thank you, Dan. You can take the rope back for now, at least. Thank you. God, you're easily impressed. Got it? Thank you. So, they took their data, they analyzed the first year of data, and in April 2021, they were ready to announce to the world the new measurement of the magnetism of the muon. And to everyone's delight, the new measurement landed bang on top of the old result from Brookhaven, which caused this to happen. So you got new headlines around the world from the New York Times, tiny particles wobble, upends the known laws of physics. Bit of an exaggeration, but okay. The BBC did a bit better, muons, strong evidence found for a new force of nature. So essentially, by measuring this property, again, with a different experiment, mostly a completely different team, they had pretty much eliminated two of the boring explanations. It seemed very unlikely now that this was just a mistake in the experiment, because you have two independent experiments that get the same answer. Also, because you now have two measurements with similar uncertainties, when you combine them, their combined uncertainty gets smaller, and that makes the probability that it's a random fluke really much, much lower. In fact, there was only now around a 1 in 40,000 chance that this anomaly could just be explained by dumb luck. So there is one explanation that we still haven't eliminated, and this is where it gets a bit murky. So here is a little diagram that illustrates the situation when the result was announced. So you have your theoretical prediction that is somewhat lower than your experimental measurement. And you can see, based on the uncertainties, these 2 points are quite a long way apart. Now, there's always a twist when you think things are going well, which is on the very same day the muon G-2 experiment published their new measurement, a rival team of theorists published a new theoretical prediction of the muon's magnetism. And their result landed much closer to the experiment. So if you believe one theory, it's a gold-plated anomaly. It looks like you're really seeing something fundamentally new that could be a clue to something very exciting. If you believe the other group of theorists, there's nothing to see here, gov, basically. So now you may be wondering how two different groups of theorists can get two different answers, and it's not just because one of them forgot to carry a 1, okay? It's much more complicated. Basically, calculating the magnetism of a muon is a very, very difficult thing to do. You have to take into account all these quantum fluctuations from 17 different quantum fields that we know about in the Standard Model. And in particular, there are a bunch of fields that are very hard to calculate. These are the fields that produce essentially the nuclear material in an atom. So these are particles known as quarks and gluons. Now, for technical reasons that I won't go into, and also ones I don't really understand that well, quarks and gluons, the theory of quarks and gluons is very, very hard to make tractable calculations in. And so you have to make approximations in order to get at the contribution of the quark and gluons fields. And these two theoretical groups use different approaches. One uses a sort of data-driven approach, and the other uses a first principle approach using a big supercomputer, essentially. So the situation we're now in is that we do not know if this anomaly anomaly really is the clue to something big, and it could be massive. So, one potential explanation for this anomaly is that the muon is being affected by what we call dark forces. So this is not something out of Harry Potter. It's actually, so we know the universe is dominated by dark matter, and in principle it's possible that just like the ordinary matter universe has its set of forces, electromagnetism and the nuclear forces, dark matter may also have its own set of forces through which it interacts. And one explanation for this anomaly among many is that dark forces are affecting the magnetism of the muon. Or it could be that we don't understand the physics of quarks and gluons properly. So to settle this story, theorists are really going to have to slug it out and come up with a consensus prediction for the muon's magnetism. So this is a classic story of how anomalies work. Sometimes they can lead to a massive breakthrough in your understanding. But even when they don't, they often improve your understanding of the current science. So even if at the end of all of this massive effort that everyone's gone to measure this tiny magnet, we find that there is no new physics, we will have learned a huge amount, not only in terms of experimental techniques, but also in terms of the physics of fundamental ingredients of our universe that we do know about. So it's never wasted effort, although of course we'd all hope that it's something exciting. So I'm now going to switch to the other end of the scale and tell you a second story, this time an anomaly that has been occupying the field of cosmology for the best part of a decade now. Now, to tell this story, I'm going to take you back in time to just after, essentially, Einstein has come up with his theory of general relativity. So back in the 1920s, there was a big debate in astronomy about the size of the universe. There were these objects that were seen in the night sky, at the time known as spiral nebulae, these kind of whirlpool-shaped smudges. And there was a disagreement over whether these swirly cloud-like things were just clouds of dust and gas inside the Milky Way, or perhaps galaxies in their own right, outside of the Milky Way itself. So at the time, the view was that the universe was one galaxy, so one island of stars amidst this endless blackness. To figure this out, you had to find a way of measuring the distances to these spiral nebulae. And this is something that the American astronomer Edwin Hubble spent a lot of time using the Hooker telescope at Mount Wilson in an attempt to unravel. Now, the problem with measuring distances in astronomy can be encapsulated by this lovely scene from Father Ted, where Ted attempts to explain to his half-witted fellow priest Dougal the differences between a small cow that is close and a big cow that is far away. Now, I'm not saying astronomers are as dumb as Dougal, but they have the same problem, essentially. And I've got a nice video that the RI demo team, Dan, prepared, which essentially is two lamps which were shone down the hallway. Hopefully, oh, actually, no, I've got this wrong. Oh, why is it not there? Sorry. It skipped a slide, apologies. So hopefully this will work. Is it going to play? No, it doesn't want to play. Let's try this. Okay, so these are two lamps. Now, they are of different brightnesses and of different distances, but I think you would struggle to tell which one's further away until the lights come on, when you reveal that one of them is actually the end of the RI corridor, the other one is much closer. So they have the same problem, that you don't know whether a star is big and bright but far away, or small and dim but close. And the person who allowed us to figure out essentially how far away stuff is in the universe, at least stuff beyond our local galactic neighborhood, is this woman. This is Henrietta Swan Leavitt. She was a pioneering astronomer of the late 19th, early 20th century, and she spent much of her time studying a type of star known as a Cepheid. So Cepheids are young, bright stars that have these pulsating atmospheres. So they grow and shrink over time. And you can see, hopefully in this animation, this star is pulsating. And so they get brighter and dimmer as you watch them through a telescope. Now, Leavitt discovered that there was a relationship between how fast this star pulsed, essentially the heart rate of this star, and how bright it was. So stars that pulsed more slowly were brighter, stars that pulsed more quickly were dimmer. And if you could calibrate this allowed you to measure distances, because you could look at a Cepheid in a distant galaxy, you could measure its pulse period very easily, because you just count, essentially you time it over a period of days or weeks, and then you know from its pulse period how bright it is, and if you know how bright it is, you know how far away it is, from how bright it appears in your telescope. So you suddenly now have a ladder, essentially, a distance ladder, that allows you to measure distances. When Hubble did this, he found Cepheids in Andromeda, which is the largest spiral nebulae in the night sky, and he found that Andromeda was 1 million light years away, far larger than the established size of the galaxy at the time. This proved that there were galaxies outside the Milky Way. Now, Hubble spent the following years, having massively expanded the size of the universe, making similar measurements to a whole host of galaxies outside the Milky Way. And he discovered this extraordinary relationship, which was that there was a relationship between how far away a galaxy is and how fast it's moving away from us. So it was observed by Vesto Slipher that almost every galaxy in the night sky is retreating from us. And he figured this out essentially by looking at the light from those galaxies. Because they're moving away, their light is what we call redshifted. It's stretched to longer wavelengths. This is the same effect you get when an ambulance goes past you in the street and its siren goes from high pitch to low pitch. The same thing happens with light. So you measure speed from this kind of this stretching of the light, and you measure distance using Henrietta Swan-Leavitt's Cepheids. And when you do this and you plot it on a graph, you find that the further away a galaxy is, the faster it's moving away from us. Essentially, what Hubble had found was that the universe is expanding. Now, I'm going to try and demonstrate this. This could go horribly wrong. So it's quite hard to imagine a three-dimensional space. So what's actually happening here is that the space between the galaxies themselves is getting bigger. Now, this is quite hard to picture, but if we reduce the universe to a two-dimensional object, it's a bit easier. So what I have here, which the RI demo team kindly provided, is a black balloon with some nice galaxies stuck on it. And I'm now going to turn on an air pump, and hopefully it won't all go bang. It will be quite loud, though. Here we go. So as the balloon grows, I'll step away, the galaxies all get further and further apart. And the further they are away from each other, the faster they are retreating. So I will stop this before I actually get a big bang. Right. So we'll just let the universe slowly deflate now. I don't know how educational that really was, but did it help? Now, so Hubble described this relationship. It became known as Hubble's law. I don't think he called it Hubble's law. I guess other people did. And it's a very simple equation. So basically, v, which is the speed the galaxy is retreating from us, is related to its distance d by this parameter h naught, which is what became known as Hubble's constant. Now, Hubble and his colleague Humason made the first measurement of Hubble's constant back in 1931, and they got this number. So this is probably rather inscrutable. They got 500 kilometers per second per megaparsec. So what does that mean? Well, it means that a galaxy a megaparsec away will be moving away from us at 500 kilometers per second. Now, what's a megaparsec? It's about 3 million light years. So it's a long way away, basically. So we're talking very large distances. We're talking intergalactic distances. The problem with this measurement of Hubble's constant was that essentially this is saying the universe is expanding very quickly. The bigger Hubble's constant is, the faster space is expanding. Now, this meant that if you rewound the clock to the Big Bang, the universe only ended up being about 1 billion years old. But if you speak to a geologist, they have a bit of a problem with this because they have found rocks that are 3 or 4 billion years old. So it appeared that the Earth was somehow older than the universe itself. And as astronomers made more and more precise measurements, they gradually realized, oh, actually, there were some mistakes in Hubble's original analysis. The number fell to 180, then it fell again to 100 kilometers a second in the 1970s. Actually, in the 1970s, there was this vicious debate between two different groups of astronomers, one who thought Hubble's constant was 100, another who thought it was 50. So this is essentially because measuring distances is hard. The difficulty here is actually the key thing you need to do is measure how far away a galaxy is, and that is very, very difficult to do, even using Henrietta Swan-Leavitt's Cepheid variables. Now, this Hubble constant is where the anomaly, I'm finally getting to the point now, is where the anomaly that occupying cosmologists lives today. But it's not this 100 versus 50, it's much more subtle than this. But just to sort of establish why this matters, the Hubble constant essentially tells us how old the universe is, and it tells us how big it is. So it's fundamentally crucial to our understanding of the universe around us. Now, this debate over whether it was 100 or 50 was finally settled by this wonderful instrument, the Hubble Space Telescope, launched at the start of the 1990s. Now, Hubble was used to make a wide-ranging survey of Cepheid stars. So here's a lovely photograph of a Cepheid taken by the Hubble Space Telescope. So you get these really beautiful measurements of these pulsating stars. And this allows you to make more accurate distance measurements. But what Hubble also allowed astronomers to do was to extend the distance ladder even further out into the universe. There comes a point where you're looking at galaxies that are so remote that you can't resolve individual Cepheids. So to measure their distances, you need a different, what we call standard candle. So this is essentially how this is done. So this is a diagram representing what we call the cosmic distance ladder. There are 3 rungs on this ladder. The first one uses a technique known as parallax. So we can use this essentially to measure distances to stuff in our local galactic neighborhood. Now, parallax may sound fancy and mathematical, but it's the thing we all use to judge distances if we have 2 eyes. So essentially, the way that we judge distances is that our 2 eyes have slightly different viewpoints, and that means objects appear slightly differently in the 2 images, and that allows us to create a sort of 3D model of the world. Now, our eyes are far too close together to be able to tell the differences between different stars, but the Earth orbits the Sun, and at 6-month periods apart, it's 300 million 300 million kilometers apart. And that gives you a long baseline, and you can use that essentially to see how stars shift in the sky and get a measurement of distance. Then you use Cepheids. That allows you to measure distances out to about 100 million light years. But then beyond that, you use another object known as a Type 1a supernova. So this is a photograph of the galaxy NGC 2525. I hope I've got that right. And this was a supernova that went off in 1994. And this is actually a picture taken by Hubble. So you can see the spiral galaxy, and then this little dot here is the Type 1a supernova. This is essentially the dead husk of a sun-like star that detonates violently and briefly outshines the entire galaxy. And it's believed that Type 1a supernovae basically all go off with a similar brightness. So if you can calibrate how bright they are, and you can see these things incredibly far away because they're so bright, you can use them again to measure distance. So Hubble made these new measurements, Cepheids and Type 1a supernovae, and it got a new measurement of the Hubble constant. Oops, a daisy. And it came out at 72 plus or minus 8. So not 100 and not 50. They were both wrong, actually. It was somewhere in the middle, which is not perhaps altogether surprising. So come 2001, the Hubble Key project had completed its work. The debate of the Hubble constant was done and dusted. Why would you bother measuring it again? We kind of know the age of the universe. We know how big it is. Fine, we could all go home. But then something happened. So in 2013, this lovely instrument, which is the Planck spacecraft launched by the European Space Agency, produced its first results. Now, Planck was a very special spacecraft. It wasn't looking at stars or galaxies. It was looking at the Big Bang itself. So Planck did a survey of what we know as the cosmic microwave background. This is the faded light from the Big Bang itself. And it produced, essentially, if you think about what we see when we look out into the universe, this is a sort of diagram representing the observable universe. We're in the middle, although we're not really in the middle of the universe, it just looks like that from where we are. And because light travels at a finite speed, the further out you look, the further back in time you look. So as you move through this image, you see the sun in the middle and the planets, then you see the Milky Way and then distant galaxies. And then as you go further and further, eventually you see this dark band. That is essentially a time before the first stars formed. But if you keep looking, you will look far enough back in time that you see the primordial fireball that filled the universe at the very beginning. Now, that would once have been a very, very bright, radiant fireball, but because of the expansion of the universe, that light has been stretched down to a very cold microwave signal, known as the cosmic microwave background. And Planck produced the most precise ever map of this radiation. Essentially, it took a photograph of the universe as it was about 380,000 years after it was born. So this is the oldest picture we can get, or sorry, the youngest picture really we can get of the universe. Now, what you're looking at here, these different colors represent regions of the universe that were slightly hotter and denser than others. So the blue bits are a bit emptier and a bit colder. The brighter yellow and red bits are a bit hotter and a bit denser. Now, these are very subtle temperature fluctuations, but by studying it, you can get a treasure trove of information about the universe. In particular, you can use this data to figure out how much dark energy there was in the early universe, how much dark matter there was, how much radiation, how much ordinary matter. And with that information, you can plug it in to Einstein's general theory of relativity, and you can run the clock forward. So essentially, you have this data from the very earliest moments of the universe, and then you can use it to predict how fast the universe ought to be expanding today. So you have these two different methods, essentially, for measuring the Hubble constant. One is using galaxies, and you measure it essentially by stuff that we can see. The other, you look at the Big Bang, and then you predict what it should be. So in principle, if your cosmological theory is right, you should get the same answer. But when Planck published their result, it disagreed. So they get a value of 67 plus or minus 1.2. When this result, and at this point, the measurement by Hubble had been updated by another team who had reduced the error substantially. So now you had these two numbers that are in really quite, noticeable tension with each other. Now, this led to a huge amount of scrutiny, particularly for the team that had used the Hubble Space Telescope, because people basically said, oh, you've got it wrong, you've misunderstood Cepheids, you've measured distances wrong. And they have basically spent the last decade drilling into their methods, repeating the measurements over and over again with more data from more telescopes to firm up this measurement of the Hubble constant. And this Hubble tension, as it's become known, has become a real crisis in some sense in cosmology. So how can you have two different measurements of the expansion of the universe that give you different answers? Well, one, again, as I said earlier, there are always boring explanations. A boring explanation is we don't know how to measure distances, for example. But the exciting explanation is there is something profound missing from our understanding of the universe. Perhaps the standard cosmological model is incomplete. There is something missing from this picture. Now, this would not be terribly surprising when you consider another name for the standard cosmological model is the lambda CDM model. Lambda stands for dark energy, and CDM stands for cold dark matter. So the two things that dominate your theory of the universe are completely unknown. So it perhaps wouldn't surprise you if there was something else that you hadn't seen. So the Hubble tension could be the clue to something new that we don't understand about the history of the universe. And that's why it became so tremendously exciting. The problem was, ultimately, that the debate over the Hubble tension came down to people not really trusting the measurements of distances based on these Cepheid stars. And as I said earlier, the cosmic distance ladder basically relies on these Cepheids to act as a bridge between stuff we can measure in our local galactic environment and much more distant stuff out in the very, very, very distant universe. If that middle rung is wobbly, then the whole ladder might collapse, essentially. So the question was, could we really trust these Cepheid stars? The reason people perhaps were suspicious of these stars is that because they are young, sort of pulsating stars, they form in the star-forming dust lanes of spiral galaxies. So here we can see a really beautiful image of NGC 5468, which is actually the furthest galaxy that we can resolve individual Cepheid stars in. It's, I think, around 130 million light years away. So these Cepheids, they live in these dust-forming regions, and if you have dust, that can block the light from the Cepheid, and that could make them appear dimmer or redder than they actually are, and that then can lead you to misestimate the size of the universe. What everyone has been waiting for with bated breath to resolve or help to resolve this puzzle is this beautiful thing. So this is the James Webb Space Telescope, or at least when it was being constructed here on Earth. It is in some sense the sort of spiritual successor to the Hubble Space Telescope. It was been decades in the making, this incredible, vast, gold-colored mirror. And what James Webb, essentially his job is to look at the universe, but unlike Hubble, which mostly looked at the universe in the optical spectrum, in visible light, James Webb looks at the universe in infrared. Now that's key. So here we can see Webb being launched. It went up on Christmas Day, 2021, which is a real sort of, squeaky bum moment, as people say in science or in other fields as well, where you have this incredible, multi-billion pound instrument on the top of a massive bomb, essentially, that's being blasted into space. But amazing, the whole thing went off without a hitch. Webb made its way out to a Lagrange point, very distant from Earth, unfolded this incredible mirror and its solar shield, and it's been making beautiful observations of the heavens ever since. And here is one of the results of Webb's observations. Here is that same galaxy, NGC 5468 again, but this time superimposing onto the visible light measured by Hubble, the infrared measured by Webb. And when the team that were measuring the Hubble constant reperformed their analysis using this new data from James Webb, their number, the number of the Hubble constant, landed bang in the same place. So this removes one of the major challenges to really believing that the Hubble tension actually is an anomaly that is showing us the way to a new understanding. So we're now in this incredibly exciting moment, actually. I think there have been many skeptics about this particular anomaly over the years. Not all of them are persuaded, but I think increasingly, from talking to cosmologists, they're becoming increasingly convinced that there really is something that we do not understand about the universe. So what could this mean? Well, one of the reasons that the Hubble tension actually took so long to be accepted is essentially there isn't really a ready-made theoretical explanation for this. Now, one of the driving figures behind this whole story is an astronomer called Adam Rees. Now, Adam Rees became very famous as one of the co-discoverers in the late 1990s of the accelerating expansion of the universe. So he and a team, and actually two different teams of astronomers, discovered that galaxies are actually accelerating in their expansion. And this led to the realization that the universe is permeated by this stuff that we call dark energy. Now, when I asked Rees, why do you think that the accelerating expansion was accepted relatively quickly, whereas this weird thing with the Hubble constant hasn't been? He said basically that back in the 1990s, there was a ready-made explanation for the accelerating expansion. Way back in time, when Einstein was putting together his general theory of relativity, he actually added an extra term to his equations that he called the cosmological constant. Now, the job of the cosmological constant was essentially to stop the universe from collapsing. Because what Einstein realized was that under gravity, the universe ought to just implode on itself, and yet it seems kind of, nice and stable and static. So he added this repulsive anti-gravity force to his equations to prevent the universe from falling in on itself. Now, when Hubble discovered the universe was expanding, there was no longer any need for dark energy because essentially the universe is getting bigger, so it's just kind of a momentum effectively that's carrying it to carry on getting larger and larger. You don't need this repulsive force. But when the acceleration of this expansion was discovered, then there was this ready-made thing. Einstein's cosmological constant gets reintroduced, and in a flash, it explains the observations. There was a ready-made theoretical explanation. This time around, there isn't one. Now, I think in some ways it's a rather odd way of looking at science to say, I won't believe the data unless there's a ready-made theoretical explanation for something. Ultimately, science is about the universe as we find it. So we can't really use our prejudices or our presuppositions to sort of decide what we include or what we don't. But it seems increasingly clear that if you want to explain this anomaly in the expansion of the universe, there isn't going to be one single solution. It may be that it's a combination of different effects. So a very popular explanation is something known as early dark energy. So a kind of force that shaped the universe in its very earliest history, around a few 100,000 years after the Big Bang, but then faded away in the later universe, but then perhaps combined with dark matter that interacts with itself in the later universe. Even more profoundly, actually, one possible set of explanations is that Einstein's theory of relativity itself needs revising, and we need a new theory of gravity. So we don't yet know how this story is going to end or how this anomaly is going to be resolved, but it seems increasingly likely that it really is telling us something big about the universe that we do not understand. So I think that's tremendously exciting. Now, these are just two stories that I've covered. There are a whole bunch of anomalies out there in the work. So the book covers actually 5 big stories that are dominating particle physics and cosmology. For example, particles with impossible energies that are bursting from beneath the Antarctic ice, and neutrinos that are turning up unexpectedly in experiments with no apparent explanation. Now, with any anomaly, the most likely explanation for it is ultimately the boring ones. Usually anomalies go away. Usually they are an experimental mistake or theoretical miscalculation or just a bit of bad luck. But every so often, they are the clue to a profound new view of the universe. And that is why I find them so exciting, and that's why I decided to tell this story tonight and in the book. So if you've enjoyed this lecture, I do encourage you to pick up a copy where you can read all about the anomalies that are perplexing physicists today, and also how they've shaped our understanding of the universe in the past. Thank you very much.